Hi, Mrs. With you back for Unit 2 video lesson number 7. Now we're going to take a look at the particle nature of light, otherwise known as the particle model of light. We've looked at the wave nature of light, which could not explain phenomena that scientists were observing with light and matter. This phenomenon included why heated objects emit only certain frequencies of light, and why some metals emit electrons when light with the specific frequencies shines on them. And these don't make sense, but hopefully by the end of this video lesson it will. In 1900, Max Planck, he's a German physicist, studied light emitted by heated objects. He concluded that matter can gain or lose energy in small specific amounts called quanta. Quantum, which is singular, is the minimum amount of energy that is lost or gained by an atom. And what we'll learn about is specifically the electron. He proposed that energy emitted by hot objects were quantized. That is, the energy is released in specific amounts. Anytime we say quantize, it's very specific amounts of energy. There's a relationship between energy of a quantum and the frequency of the emitted radiation, and this is it. The energy of a quantum is equal to h times the frequency, where h is Planck's constant. Just like the speed of light is a constant, h is a constant too, and that is equal to 6.62 times 10 to the negative 34th joules, which is our energy unit, times second. So the energy of the quantum is equal to Planck's constant times the frequency, nu. Scientists also observed another phenomenon called the photoelectric effect that couldn't be explained by the wave model of light. And wave model simply says that light travels in waves and has a certain amount of frequency associated with them. And so the photoelectric effect, what that was, kind of like the cathode ray tube, where you have a cathode and you have an anode, and instead of like passing electrical current through it and getting a beam of light, you shine light on the metal, on the cathode. And when you shine the light on the cathode, then you had a beam of electrons was being released from the cathode. And so that was the phenomenon, is why when you take light of a certain amount of energy, you take that specific amount of energy, light energy, shine it on that metal, and these electrons are being released. And that was something that scientists couldn't explain with just light traveling in waves. So these electrons are released from the metal when light energy strikes the surface of the metal, is the photoelectric effect, a definition for it. Concluded that electrons will only be released or ejected from a metal when the light has a specific amount of energy that is higher than the energy possessed by the electrons that were being released. In 1905, Albert Einstein proposed that light has a dual nature. And what that means is that light is both wave-like, like it travels in waves, but it also has a particle-like behavior. And that was something that was outstanding or astonishing to be said at that time, because light is energy, and energy isn't made up of particles. But Einstein is proposing that light has this dual nature, both wave-like and particle-like behavior. So what he said is that light can be thought of as a beam of bundles of energy called photons. Photon, also called a particle of light, is a massless particle that carries a quantum of energy. So you have a photon of energy, a particle of energy. Concluded that a photon's energy depends on its frequency, and thus a photon with a specific energy will only eject electrons with the same amount of energy. The energy of a photon equation is something that Albert Einstein won a Nobel Prize for in 1921, and is equal to, the energy of a photon is equal to Planck's constant times the frequency. And we're going to use that equation to solve the next couple of problems. So here's the first one. Every object gets its color by reflecting a certain portion of light. The color is determined by the wavelength of the reflected photons, thus by their energy. What is the energy of a photon from the violet portion of the sun's light if it has a frequency of 7.230 times 10 to the 14th hertz? So our given unknown and plan is frequency is equal to 7.230 times 10 to the 14th hertz. The unknown is the energy, and the plan is simply the equation. Energy is equal to Planck's constant times the frequency. We're going to plug in those numbers and then solve for the, and so the answer to 4 significant figures, because 7.230 has 4 sig figs, is 4.786 times 10 to the negative 19th. Now, if hertz is 1 per second, then seconds divides out, and that gives us joules, and joules is the energy unit, and that makes sense. The next problem, new sunscreen is reputed to protect against UVA waves that can cause skin cancer. How much energy is possessed by a single photon of UVA with a frequency of 9.231 times 10 to the 14th hertz? Okay, so the given, the unknown, and the plan is the frequency is equal to 9.231 times 10 to the 14th hertz. The unknown is the energy, and we're just using the energy equation. Plug in the numbers, multiply them, and solve for the answer. And again, to 4 significant figures, the answer is 5.834 times 10 to the negative 19th joules. Okay, again, the hertz would be 1 per second, so seconds divides out, that leaves us with joules. All right, so that's the end to video lesson number 7. This is Mrs. Wheathy, so long for now.